Before we consider covalent crystals, let us revise some of the previous concepts with regard to covalent metallic and ionic crystals, especially with regard to the bonding in these crystals. So let us look at covalent crystals first. We know that electrons in a covalent crystal are not localized near the ion cores. Suppose we have the positive ion charge near the nucleus, the electrons are not localized there, and in fact the region between the ion cores, the electron density is not uniform, and typically it is like which is the example of uniform density between the ion cores would be a metallic example, but you would notice that there is a preferential direction between the ion cores wherein the electron density is very high. So this is very simple to look at the picture and understand more than in words. So the typical structure of column 4 elements, for instance, we know these carbon, germanium, silicon and gratin have a diamond cubic structure. So let us look at the electron picture to understand how does a covalent bond look. So you know in a covalent crystal that the electron density, unlike a metal, for instance this is a metal, and you know that there are these positive ion cores, and between the cores the electron, which is called the sea of electrons, the electron density is practically uniform. Of course there could be some non-uniformity, but it is practically uniform. On the other extreme is the covalent ionic crystal, wherein all the what you call the charge is localized around the ions and there is not much charge in the interstitial region. The covalent crystal is a special case of this kind of presence of interstitial electron density, and this is, as you can see, localized along the direction of the bond. So this is what we typically call the interstitial high electron density is what we call the covalent bond. So you can see that here between the ion cores. So the ion cores are positioned here and you have this interstitial region along certain direction that you find the high electron density, which we call the covalent bond, and which is in sharp contrast to the metallic crystal where the electron density is uniform, or the ionic crystal which is shown below here, wherein you find that the electron density is localized around the ion cores. So covalent crystals are very different in that sense from metallic or ionic crystals, but then we will also try to understand how we can have a smooth transition from, or a continuous or a continual transition from covalent to ionic kind of bonding. The ionic crystals, as we have seen, is composed of metallic and non-metallic elements for in simple cases. The electronic charge distribution is localized near the ion cores, and in this case we can consider the bond as one of the species donating the electron to the other species. So one of them becomes negative, the other one becomes positive, and there is an electrostatic attraction between the positive and negative ions, which we call the ionic bond, okay, or the ion, and which finally leads to the formation of the ionic crystal. In the simplest case, we can assume that these ions behave like hard spheres. In other words, if you have a donation of an electron, the electronic configuration is complete, this closed shell is formed, and when another ion is if we try to push another ion into the same region, then according to Pauli's exclusion principle, these have to go to a higher energy level, and therefore there is a strong repulsion, and in the simplest case this kind of a repulsion can be thought of as an hard sphere repulsion case, okay. And the closest that one gets to a pure ionic crystal are the alkali halides, which are formed between the group 1 and column 1 and column 7 elements. Now we will also see, as we saw, that we will be talking about two important transitions: transition from a purely ionic to a sort of a covalent bond, and also transition from the type of bond like ionic to covalent to metallic to molecular kind of a crystal, okay. So these two kind of things we will focus now. So in these alkali halides, typically the positively charged ion could be lithium, sodium, potassium, rubidium or cesium, and the negatively charged ion, which is a singly charged negative ion, could be fluorine, chlorine, bromine or iodine. So you could have an ionic crystal, for instance lithium fluoride or sodium chloride, which we have seen the structure of before, and these sodium chloride, for instance, come as close to an ionic bond as possible theoretically, and in this case you can treat almost the what you might call the model of the ion as an hard sphere model of the ion, okay. Typically these structures, as we have seen for the case of sodium chloride, are all mostly they are NaTl type of structures, but there are exceptions like for the case of cesium chloride, cesium bromide, which we have seen form a simple CaCl kind of structure. So this is a simple cubic structure instead of a face centered cubic structure. There are cases in which the positive ion is so small that it can be assumed that the negative ions almost touch each other, and therefore when you make the lattice parameter calculation, we practically ignore the positive ion in making the lattice parameter calculation. So, this alkali halides, as I said, are perhaps the example of what you might call a nearly perfect ionic bond, wherein all the charge is localized around the ionic cores. If you go to the 2,6 column ionic crystals, you will notice that the bond is ionic, but still here it is, even you make an hard sphere approximation to the ions, it is not that perfectly obeyed. And they, for instance, the ions which can form, this could be beryllium, magnesium, the positive ion, calcium, strontium or barium. The negatively charged ion could be oxygen, sulfur, selenium or tellurium. And typically, for instance, you could have an magnesium oxide compound forming. Now, this magnesium oxide crystal, typically most of these go into the sodium chloride structure, except for these beryllium compounds and magnesium telluride, which do not have the sodium chloride structure. And these beryllium compounds, for instance, they have the zinc blend structure, which is telling you, as we already seen in the zinc blend structure, that it is tetrahedral bonding which is dominating, right. That means that the ionicity is slightly reduced now. It is not that ionic as a purely sodium chloride kind of a structure, which is true for the previous cases, which is the 1,7 structures. So, the 2,4 structure already is what you might call a little stretch on the pure ionic character of the bond, and you could often see that the structure stabilized is not characteristic of a pure ionic crystal. And you can see that beryllium and is difficult to ionize, and the bonding is not ideally ionic, and therefore they choose the zinc blend kind of a structure. Now, when you go to the 3,5 crystals, the bonding is practically now cannot be even called ionic. It is typically put under the covalent kind of a bonding, and the bonding is what you might call covalent with a little bit of ionicity. So, now we are starting from a pure ionic bond, we have transitioned into the 3,5 crystals, wherein the bonding is what you might say more covalent than ionic in nature. So, for instance, the ions which can contribute to this kind of a formation of ion crystal is aluminum, gallium, indium, which are the positively charged ions, and the negatively charged ions could be phosphorus, arsenic or antimony, and for instance, you could have an aluminum phosphide. And the important compounds here, for, as you know, are many of them are semiconductors. They are technologically very useful compounds like gallium arsenide or indium arsenide, and these typically crystallize in the zinc blend structure. So, we have a lot of important technologically important semiconductors coming out of the 3,5 crystals, and this zinc blend structure further emphasizes the covalent character of the bond. And these semiconductors which form from these typically have a small band gap, and this is because of the weak ionic nature and these electrons not being strongly localized. So, as you go, even in the ionic crystals, as you go from the 1,7 to the 2,6 to the 3,5 compounds, you can see that the ionicity is reducing, and slowly that reflects in the kind of crystals which form, the kind of crystal structure which is finally expressed by the combination of ions. Now, we have already seen this picture, and we have seen that how the electron density distribution is taking place around the ion cores and in the interstitial region. So, the extremes, as I pointed out, are the metallic crystal, wherein there is a uniform distribution of negative charge in this, which we call the sea of electrons. The other extreme is complete localization of the charge around the ions, which is the case of the ionic crystal, but somewhere in between, wherein there are directional distribution of charges. That means electron density is not uniform, but it is also not localized, but especially is directed along the ion cores along certain directions. For instance, in the germanium or carbon diamond structure, you would notice that it is along the tetrahedral directions around a single carbon atom. So, that would be a covalent kind of a crystal. Now, we also talked about something known as the molecular crystal, and in that case, as you know that these individual entities are molecules, which I am shading here. So, this would be a molecule, for instance, and now the interaction between the molecules is of a weak type. There is a weak interaction which is actually leading to the formation of a crystal. Okay. So, typically because the interaction which is weak, which is giving rise to the crystal, the melting point would be lower, okay, and this is a characteristic of molecular crystals. So, we will take up at least one definite example in this set of lectures regarding what is a molecular crystal, but we already considered quite a few examples of ionic crystals and metallic crystals, and we will proceed in this set of lectures with the covalent crystals next. Yeah.
Sir, here you are talking about crystals. So, these are only hard sphere interaction or soft sphere interaction also there? Is it, can we distinguish between them? on the basis of metallic crystals or not?
Okay. I am not quite understanding what you mean by a soft sphere interaction, but let me guess what you mean by a soft sphere interaction. In this case, what we mean by a hard sphere interaction is what is said here in this slide here. In other words, if I approximate my ion to be a hard sphere, that means that there is a region from which another ion cannot approach. So, for when there is two ions are far away, it is purely an electrostatic attraction, okay. But when it comes closer, it stays in attraction, but after a certain distance the repulsion goes to practically infinity. So, this is what I mean by a hard sphere repulsion. It is not the kind of 1 by r power 6 or those kind of attraction repulsion cases. So, it is not like
this case also comes in some polymer, soft materials like polymers. So there is also one certain distance, after it they cannot approach to each other.
Yeah.
So this is always exist in all particles, but if you consider in hard sphere, so that is I think too much similar, both things are too much.
I do not know, when you use the word soft,
yeah.
I do not know in what context you are using. For instance, suppose we use the word soft condensed matter. So,
Yeah.
In that context there is some difference between the meaning we are using for hard sphere compared to the meaning perhaps which you imply from a soft material. So, but yeah, in many cases you can use a hard sphere approximation for an ion or for a metal and it would work very well for you.
Such consider one suspension, maybe one particle of any particle consider suspension. So this is hard sphere will be or soft sphere.
Okay. Now, the question is that what kind of an interatomic potential are you modeling? This is what we are asking. Okay. Now, suppose I model an interatomic potential in which I have an attractive regime, but the repulsive regime is also a certain kind of a polynomial, certain kind of a power function, so 1 by r power n kind of a function. Then there is no problem. This is a soft sphere in repulsion and a soft sphere in attraction. So, there is a region of influence of the two spheres. But suppose I model the repulsion as if it is 0 for a certain distance and infinity for a certain after a certain distance, then that I call a hard sphere model. Now, at least approximately. Now, to understand more for instance quantitatively what is meant by the ionicity of the chemical bond, if you look at the for instance the electron density midway between two nuclei, in the case of sodium chloride for instance, which is as I said is a very good example of an ionic bond, the electron density is 0.1 electron per angstrom cube. It is a very small electron density between the ion cores, but in the case of carbon, which is as you know is a covalently bonded material, the electron density is 5 electrons per angstrom cube. So, there is considerable electron density in the inter-ionic regime in the case of the covalent bond, which is clearly seen from the actually considering the electron density between the two ion cores. So, the next slide for instance we consider a progress from a, for instance what you may call a nicely covalently bonded material to a case which is perhaps an ideally ionic material. So, an ideally covalent bonded material, for instance we know germanium crystal which crystallizes in a diamond cubic structure. So, this is just a schematic, please do not actually try to understand it in terms of the diamond cubic structure, this is just a schematic. So, I should actually have replaced this with any n plus, okay. So, that should have been a better example. So, you see this is a perfectly covalently bonded material. But if you take another case, again this is being a schematic and not actually trying to explain the actual structure. So, this is a gallium arsenide. So, gallium 3 plus and arsenic 5 plus are the ions, and you can see that this has an ionic character, but this has a covalent character, but these two ions being different, there is a slight ionicity to this bond. Even more ionic kind of bond would be between calcium and selenium, the calcium 2 plus and selenium 6 plus. So, you can see that these are the charges are, there is a disparity in the charges. That means that the localization is not perfect and there is a certain distribution of electron density in the that means there is a certain localization and there is also a certain delocalization. So, both are there here, and therefore, this is somewhere between a perfect ionic bond and some between a perfect covalent bond. Of course, you can have a perfect ionic crystal like which is the KCl crystal, and in which the K plus and Cl 7 plus, they are the two ions, and you can see that the electrons have been highly localized in this case. So, in this is perhaps a nice schematic slide, though we should not read into the exact structure or even perhaps the exact electron density, because as you know this perhaps this surface here, what this actual line might represent would be a certain electron density. So, this configuration which you see here, this outline actually perhaps represents a certain electron density. So, if you, so this would for instance suppose this represented say 0.05 electron volt, then there would be a contour which would go inside this, which would have a even lower electron density. It does not mean that it straightly abruptly goes to 0 here. So, there is a distribution of electron density progressively going to 0 somewhere perhaps in the region which is at the center. So, we have to be a little careful in interpreting these diagrams, but the overall message, which is sort of the purpose of this slide, is the understanding that you can have purely covalent bonding, you can have a slightly ionic nature to this covalent bonding, you can have bonding which is somewhere in between an ionic and covalent bonding, and finally you can have a bonding which is purely ionic kind of a bonding. So, all these possibilities exist, and therefore, the structure we have seen, even the special example we saw that we we use the Pauling's rules or the rules for the understanding the formation of ionic crystals, and we said when we took up the structure of zinc blende, we could no longer rationalize that kind of a bonding based on the rules of the ionic crystal. So, we had to go to more, it had more covalent character, therefore, it had to be the kind of bonding was a tetrahedral kind of bonding. So, now we are in a position to take up covalent crystals, having understood that there are of course these perfect covalent crystals, but there are other crystals which have certain ionicity to the bonding. So, of course, we already know the characteristics of a perfect sort of a covalent bonding. The covalent bond is highly directional and they are very strong, typically they have very high binding energies, and the various forms of carbon which we will take up the examples, and some of them we have already considered, are perhaps the best examples to understand covalent bonding. Okay. Now, carbon, needless to say, is perhaps the most important element, it is the source of all life, but with regard to even formation of crystal structures, you can note that its role is very, very important. Not to say even as an alloying element in steel, which perhaps we will see later in the course, that it can give a lot of hardness to iron, and the steel is a very hard form, especially when it forms a phase called the martensitic phase. So, carbon is very, very important, and the important allotropic forms of carbon we know are diamond, we know graphite, and we will also consider fullerene today in today's lecture. There are other forms of carbon which are also very lot of important research, from the single sheets of which you isolate from graphite, which are called graphene sheets, is a topic of intense research now. There are nanotubes of carbon which are also a topic of hot research, and therefore, carbon is all the more in a lot of focus and attention in academia nowadays. Okay. For instance, when you have diamond has a 3D network of covalent crystals, covalent bonds. Graphite has in plane covalent bonding, while the bonding between the sheets is of van der Waals type. So, you can see already when you go from diamond to graphite, the bonding character changes, and this also changes its properties. For instance, diamond is nearly a perfect insulator, electrical insulator, though it is a good thermal conductor, it is an electrical insulator, while graphite is a good electrical conductor, and this is coming from the pi orbitals which exist and which can conduct electrons. The other example which I told you, fullerene, which we shall take up in considerable detail today, is a molecular solid. So, this is an example of a molecular solid, and this has not to be confused with the other cases of solids like the covalent crystals. So, even though we are in the topic of covalent crystals, we will take up an example of a molecular solid within this, because it is a beautiful example made of carbon, and we will see that typically it can have an FCC crystal structure or a simple cubic crystal structure, depending on if it is the orientationally ordered state or the orientationally disordered state. So, we will take up C60 also in detail, even though it is not an example of a covalent crystal. So, please remember once again as a warning that even though we are talking about covalent crystals, we are taking up this additional example of fullerene to understand the case of molecular crystals, and this one example of fullerene will throw into light many other important concepts, some of which of course will be a revision of what we have already studied before. So, if you look at the crystalline forms of carbon, as I said, graphite, which is sp2 hybridized, diamond, which is sp3 hybridized, and diamond, of course, there are two forms of diamond, the cubic and hexagonal form. So, we will basically focus on the cubic form, and of course, we already done so in considerable detail before. So, today this will be just a revision of the previous considerations, and of course, the additional one which is fullerene, and the important note that fullerene does not have pure sp2 or pure sp3 hybridization. So, that is because now if you had a flat graphene sheet, that would be sp2 hybridized, while this is a case of a graphene sheet being which is bent, and therefore, the hybridization is not purely sp2. So, examples of diamond cubic crystal structures, many of which we have already seen, like the silicon, germanium and gratin. There are compounds, important compounds in silicon carbide, which is a very hard phase and which has important technological application. We have seen the semiconductor examples like aluminum phosphide, gallium arsenide and indium phosphide, and there are oxides also like zinc oxide, zinc sulphide and cadmium sulphide, which are also very important technologically. So, there are many examples of structures which go into, that means elements and also compounds, which are all, these are all compounds which go into the diamond cubic structure. Since we have already taken up the case of graphite in detail before, the structure of graphite, perhaps this will just be a small brief revision. I will go through this topic very fast, including the case of the diamond, but nevertheless these are important structures to consider. So, we have noticed that the properties of graphite are strongly dictated by the kind of bonding, the in plane covalent and the out of plane or between the graphene sheets, the van der Waals type of bonding. Okay. And we had seen that it is about 1,000th as strong, okay, 100th as strong as the covalent bond. And the in plane electrical conductivity is high because of the kind of bonding. Okay. So, we had seen that first we need to understand the structure of graphite, we need to understand the in plane structure, and we already drawn, for instance, this was the unit cell of the in plane structure. So, this is my in plane unit cell, and we had considered this in terms of the language of the lattice and the motif. Then we went on to draw the 3-dimensional structure of this graphite, in which we had noticed that we had to actually stack the planes which are staggered with respect to each other, and you get half the repeat distance, which is shown here in the green and the blue colored planes. So, all this we had already seen. So, I am just glossing over this topic of understanding of the graphite units, graphite structure. Similarly, we had also seen diamond in detail. We had noticed that it has got an FCC lattice and there is a 2 carbon atom motif which actually decorates this lattice. Okay. And we had also noticed that, for instance, if you look at the diamond cubic structure, the tetrahedral bond actually pervades, and we had cited this as an example wherein there are no close pack direction, no close pack planes, and the structure itself was not a close pack structure. Additional thing we tried to understand using for the structure was the fact that actually the concept of what is known as the diamond glide, which is present in these structures, the D which is present, as you can see, in the space group which is drawn below. So, you can see that there is the diamond glide, and also we try to understand that why this is called a cubic structure even though it has no 4-fold axis, and what is the kind of axis which is really got, and we note that it actually had a 4-1 screw axis. Okay. So, this part we had noted before. So, this is perhaps the right time to also consider this molecular crystals, and we will consider the example of fullerene. So, what are molecular crystals? When we classified crystals, we said there are 2 types of crystals. One are molecular crystals, and other are non-molecular crystals. In non-molecular crystals, we had seen the metallic, ionic and covalent crystals. We had said molecular crystals are those crystals wherein the bonding within the molecule is typically covalent, but the forces or the bonding which is giving rise to the formation of the crystal is typically of a weak type, which could be van der Waals or some other kind of weak interaction, and one of the other interactions possible is hydrogen bonding. So, common examples of for instance a molecular crystal would be the ice crystal. In ice crystal there is covalent bonding between the oxygen and the hydrogen atoms, but the forces giving rise to the formation of the crystal is the hydrogen type of bonding, which is and you know this is a very special kind of bonding wherein you actually ice expands on freezing, which is very, very important, as you know, because if ice actually contracted on, it would be heavier than water, it would sink, and perhaps all the oceans would freeze up, while because ice actually floats on freezing, actually it itself provides the insulating layer and the remaining water remains not frozen, which is important from the point of view of life. So, the other example of an important molecular crystal is fullerene. The fullerene has to, if we want to understand the fullerene crystal structure, we should start with the C60 molecule. So, let me show you an example of a model, for instance, of a C60 molecule. So, I have here a model of the C60 molecule. To understand this structure of the C60 molecule, which is very similar to the structure of a football, I can start with an icosahedron, and you know as from before the icosahedron has 5-fold axis, 3-fold axis and 2-fold axis. So, if you connect the opposite 2 edges, you get a 2-fold axis, and there are 3 orthogonal 2-fold axis. For instance, this would be a 2-fold axis, the one vertical would be a 2-fold axis, and the third orthogonal axis can also be a 2-fold axis. Now, if I start with an icosahedron and then truncate my vertices, I truncate all the vertices, then each one of these vertices will become a pentagon. These originally triangular faces will become hexagons. Therefore, now you will have pentagons surrounded by hexagons. That means no two pentagons will touch each other. Actually all the pentagons will be isolated and you will have hexagons around it, and that is the structure we are seeing here. So in terms of rotational symmetries, an icosahedron is identical to the Fullerene molecule, which is a truncated icosahedron. So this geometrical solid you can see again has these threefold axes which pass through the top, and there are these pentagons which are seats of the fivefold axis, and of course you have the twofold which are the vertices, edges. Now it is important to note that these pentagons are isolated from these hexagons, and as we shall see very soon, the kind of bond which is present between a hexagon and a pentagon, this kind of a carbon-carbon bond. So carbons are present on all these vertices in a Fullerene molecule. Therefore this is called a C60. There are 60 of these atoms in this, and you could have higher analogues of C60 like C70 etc., but we will consider the simplest one, which is C60 or the most common one. So you can see that carbon atoms are present in all the vertices. So the kind of bonding between carbon-carbon which is here is different from the kind of bonding carbon-carbon which is between a pentagon and hexagon. In other words, if you consider a hexagon, then you have carbon-carbon bonds which are shared between a pentagon and hexagon, and there are carbon-carbon bonds which are shared between a hexagon and hexagon, and these two carbon bonds are different, and as we shall see from this slide. So let us start by considering the icosahedron, which is shown on the bottom lower part of the slide. So if we talk about an icosahedron, as here you can see that an icosahedron has 12 vertices, 30 edges and 20 faces, and this follows the famous Euler's rule for convex polyhedra. So this you can see that when I cut these 12 vertices, therefore I will get 12 more of these faces which form, okay. So apart from the original faces, so I will get my here total 32 faces, which is what you see in the case of the truncated icosahedron. The edges, as I pointed out, are of two kinds here, unlike the icosahedron which had a single kind of edges. So in an icosahedron all edges are identical, right, and that is important to note, while in the case of the truncated icosahedron we have two kinds of edges, and this has to be noted: the edges which lie between hexagon and hexagon, the edges lie between pentagon and hexagon. So the edges can be of two types: the E56 edges between the pentagon and the hexagon, there are 16 number; the E66 edges, 13 number, there are total 90 edges. The vertices have to be 60 because that is why we put 60 carbon atoms along the vertices, and I get a C60 molecule. The faces again obvious are two types: the pentagonal faces are 12 in number and the hexagonal faces are 20 in number. So this also illustrates the principle that when you have pure hexagons tessellating space, then you can only tessellate Euclidean flat space, that means two dimensional Euclidean space, and whenever I have to introduce curvature into space, then I need to introduce pentagons, which is also very clear from looking at this molecule. So this Fullerene molecule is, in other words, a single example from which we can understand many concepts, and one of the concepts we will start by understanding is of course the structure, the geometry, the symmetry, and the concept of convex polyhedra and the concept of truncation. Then we will also try to understand the concept of orientational order disorder. We are also trying to understand the concept of a molecular solid. That means we have it's the van der Waals bond which is giving rise to the formation of a crystal. So there are many concepts we can understand by considering a single molecular crystal, which is the Fullerene crystal. Now these Fullerene molecule can be approximated to a sphere of diameter 7.09 angstrom, and why this approximation needs to be done we will see when we actually talk about the Fullerene crystal. So that will become obvious that why we need to approximate this, why and or under what circumstances this can be approximated to a sort of a sphere. Now as I said that carbon is bonded to other carbon by two kinds of bonds. Casually sometimes these bonds are called for instance the double bond and the single bond, but looking at more carefully, so we will note that these are actually not single and double bonds. So sometimes casually these are called single bonds and double bonds, but looking at the length of these bonds we have to be a little careful that these are not the true lengths which are normally found for double bonds. For instance, single bonds are 1.54 angstroms in length, carbon, and double bonds are 1.32 angstroms, but here you will note that the longer bonds which are like the single bonds are 1.46 angstroms in length, and the shorter bond is which is something like a double bond is 1.40 angstroms in length. So though we might say they are double bonds and single bonds, what we mean is that these lengths are followed rather than the conventional lengths which are shown at the bottom. So, the longer bonds fuse pentagon to a hexagon, and the shorter bonds, which are 30 in number. So, 30 shorter bonds and 60 longer bonds, the 30 shorter bonds fuse to hexagons together, right. So, let us try to identify on the figures below, which there are three figures of this fullerene molecule, one with the 5-fold coming out of the plane of the slide, there is a 3-fold coming out of the plane of the slide, and also there is a 2-fold coming out of the plane of the slide, and of course, there is a model with hard sphere carbon atoms, wherein you can also identify the 3-fold direction. So, where are the double bonds and the single bond in this picture? So, the shorter bond is the double bond fused to hexagons together. So, if I am talking about a hexagon bond, so this is my double bond, and the single bond, sorry, I did it wrongly, because this is now fusing a pentagon to an hexagon. So, this is a single bond, this is a single bond, and this is a single bond, and this is a single bond, and a single bond. So, the pentagon is formed by single bonds, but when I am talking about hexagon, that is a double bond. So, this is my double bond. Okay. So, I have single bonds and double bonds in the structure, and that is why this structure is not a regular truncated icosahedron, because the bond lengths are different, the edge lengths are different. So, this is a slightly different truncation. It is not the truncation wherein you obtain. If I did a truncation, of course, I could do various kinds of truncation of this icosahedron. For instance, if I truncate a little bit, then I will get very small pentagons and large hexagons, which are not regular hexagons, right. So, this is that kind of a structure where the truncation is not exactly in a way. Suppose I truncate a little more, such that this edge, which is formed by the truncation, to the original remaining edge are both equal, that would be a regular truncated icosahedron. But the truncation in this case has been done in a way such that now my truncated icosahedron is not a regular truncated icosahedron, and the two edge lengths are different, and that means that I have double bonds and single bonds decorating this C60 fullerene molecule. So, we have to remember now, so far we have not considered the crystal, we are just dealing with the molecule, and as I pointed out, in this case the bonding character is somewhere between sp2 and sp3. If you had simple graphene sheets, the bonding character would be sp2 hybridization, but now you are bending these graphene sheets, and therefore, the bonding character is changing and it is not purely an sp2 hybridized molecule. So, the total number of rotational axes, you can see there are 6 5-fold, 10 3-fold, and 15 2-fold axes, and you will see the various perspectives along the 3 important symmetry directions of the fullerene molecule. So, to revise the fullerene molecule before we proceed to the fullerene crystal, the fullerene molecule is completely a separate form of carbon, and perhaps fullerene nanotubes, etc., are some of the important exciting examples of other forms of carbon apart from diamond and graphite. So, in some sense, fullerene molecule can be considered as a sort of a buckled form of the graphene sheet, though, but you can see clearly that to do so you need to introduce pentagons, and you cannot have a structure with purely hexagons. And in many of the what you call understanding crystal structure, we can approximate this to be like really like a football, in other words like a sphere of about 7.09 angstrom in length. So, we will start with this fullerene molecule and try to understand the formation of the fullerene crystal. So, if you consider the various crystalline forms of fullerene, we can identify basically 3 regions with respect to temperature. The high temperature, which is of course including room temperature, is a temperature regime higher than 260 Kelvin. You can see that the structure of fullerene crystal is an orientationally disordered form of fullerene, which has a symmetry of F4 by M 3 bar 2 by M crystal. So, it is nothing but a normal FCC crystal. So, instead of having a motif which would be say a copper ion or a aluminum ion, here now you have an entire molecule which is an motif. Okay. And therefore, and if what is sitting at the conventional lattice positions of the FCC lattice, there are no atoms. In fact, it is a centroid of this fullerene molecule which is occupying the position of the lattice point. In other words, as I pointed out before, this will be a nice example also of a case wherein there are no atoms sitting on lattice points, but each lattice point is associated with a fullerene molecule. So that is one of the concepts also clarified. So what do I mean by this orientationally disordered phase, we will see soon, but before that we will complete the other kind of phases which the system forms. If you look at the temperature regime between 260 Kelvin and about 90 Kelvin, you actually find a partially ordered, partially orientationally ordered kind of a Fullerene structure, wherein the structure of the Fullerene molecule jumps or between two orientations. There is still partial orientational disordered, and therefore this is still not an fully ordered crystal. And of course the parts where there is, actually this should be drawn here, the fully orientationally ordered crystal is the one which has actually the P2 by 1 by 3 bar symmetry. In other words, so let me draw this here. So this actually belongs to fully ordered state, orientationally ordered state, and this crystal, that means, lowers its symmetry from the high symmetry. So this is my high symmetry region. So this is my high symmetry phase, and this is the low temperature phase which is below 86 Kelvin, and this is the low symmetry phase. The high symmetry phase is the orientationally disordered phase, and the low temperature phase is the orientationally frozen phase, or it is a orientationally ordered phase. We had considered one example of an orientationally ordered structure, but this is perhaps an even more interesting example of an orientational order disorder transformation. So let us look at these two structures specifically, and the one which is the high temperature one, the one here, and the low temperature one which is here, which is the orientationally ordered structure. So let me first try to understand the orientationally disordered phase, which has got the symmetry of the perfect or the cubic lattice itself, which is 4 by m, 3 bar, 2 by m. Now in this case, why can we now approximate it to a sphere? Because if we are putting anything of lower symmetry than a sphere, of course now we know from our knowledge of crystallography that I need to look at not only the motif decorating the lattice point, but also the orientation of the motif decorating the lattice point, and clearly this has symmetry which is not consistent with the cubic lattice. That means the symmetry of the structure, if you put this, for instance, Fullerene molecule, say for instance the two-fold upwards identically at every lattice point, even in that case you would actually get not the f 4 by m 3 bar 2 by m symmetry, but you will get a space group which is f I think 4c, or one of those symmetries. Let me see what you will get, a f 3 bar. The second place has to be a 3 bar, so it will be the symmetry of that structure will be f I think m 3 bar. So I think this will be the symmetry of the space group with which you will obtain the structure. In other words, even if you put a sphere of Fullerene identically every lattice point, you will not get the highest symmetry possible for the FCC lattice. But now suppose I now ignore the orientational symmetry, and how can I do it? You can do it because if you notice the Fullerene molecule at room temperature, for instance, example given here at 280 Kelvin for instance, you would notice that the molecule is rotating, and the average rotational period is of the order of 10 picoseconds. So the molecule is consistently rotating, and therefore we can approximate this molecule to be a sphere. That means this orientationally disordered phase, what I mean is that this molecule is rotating, and therefore because of the continuous rotation of this molecule with about a period of 10 picoseconds, I can assume that this is a sphere, and therefore I can assume that spheres are decorating the lattice points in an FCC lattice, and therefore I can now the orientationally disordered phase, in other words, I am actually, if of course I freeze my time picture, I would get a certain orientation of all of these truncated or the Fullerene molecules. Now that, as you can see, would be perhaps a glass. A true description of that would be a glass. But now if I ignore the orientational symmetry, in other words consider this spherical orientational symmetry, consider this as a sphere, then this crystal would have this kind of a high symmetry, and this is nothing but the orientationally disordered phase of FCC crystal or of the Fullerene molecule. Now of course even this orientational complete approximation with sphere is an approximation. In reality you will note that the molecular electron density is not isotropic. That means there are some preferred orientations to this electron density, and additional complications arising that the nearest neighbors are not rotating freely, but they have some correlations. So even this model of a freely rotating sphere which is totally uncorrelated with its neighbors is an approximation, but that is a good approximation in most circumstances, and we can assume this crystal to be having a symmetry f 4 by m 3 bar 2 by m, which means it is an FCC crystal. Okay. And added to this, you can notice that apart from the point I noted out that no atom is actually sitting on the lattice points, this will be an extreme example or a very good example of a case wherein you have an FCC crystal, but it's actually nowhere near close packed. Of course, if I consider this as a hard sphere, yes, these hard spheres are close packed, but if you look at the packing fraction in terms of the volume occupied by the carbon atoms, then this will have an extremely low packing fraction. So, depending on the definition of the packing fraction, and of course, I am using a definition now that the carbon volume occupied by carbon atoms with respect to the total volume available in the crystal, then this will be a very poor packing of atoms in space. In other words, even though this is a FCC crystal, this is definitely not a close packed crystal. So, this is further emphasizing some of the points we had already considered during our earlier lectures. The lattice parameter of this crystal is 14.17 angstrom, which is a large lattice parameter. The space group we already seen. The carbon C66 distance is about 10 angstroms, okay, the center to center distance that is, and the volume of the unit cell is pretty large, which is about 711 angstrom cube. So, this is the orientationally disordered structure of fullerene. Okay. So, what we saw that when the orientations are frozen in, and now this is not randomly frozen in orientation, but there are very specific orientations into which it gets frozen, and the orientationally ordered phase actually has a lower symmetry. That means the symmetry is lowered when you have orientational order, which we already seen before. The disordered phase typically is of the higher symmetry and the ordered phase is of lowered symmetry, and this is an example with respect to orientational order and not with respect to positional order. Now, so to have it still call it a cubic crystal, we need to have this 3 or 3 bar axis, and this is still the original 3-fold axis of the molecule, which is the Fullerene molecule. The Fullerene molecule, of course, in the intermediate regions, if you want to consider some of the details, actually there are two preferred orientations, and one of them is energetically favorable, and as you go to lower and lower temperature, the preferred orientation, energetically preferred orientation sort of freezes in more, and that preferred orientation would have, for instance, these two Fullerene molecules in two different orientations. One orientation would be all the Fullerene molecules located at the lattice point corners, that means the cube corners, and the ones which are located at the phase centers would have a different orientation. And actually these two positions are actually connected by a glide if you want to look at the details. Therefore, the Fullerene molecule now has two orientations, and that means no longer it is an FCC crystal, it is actually a primitive crystal, and the Fullerene molecule which is now located at the phase centric position go part of the motif, and they are no longer lattice points. So, that point has to be noted, and the symmetry of now this structure has been lowered because of this orientational order. And if you want to look at specifically at the order of the molecule itself, there are two orientations into which the molecules are frozen in, and we can understand these two orientations as those orientations which are located at the cube corners, and the other orientation, for suppose I call this orientation 1. So, this is my orientation 1 and this is my orientation 2. So, you can see that, let me draw this on the board, maybe that is clearer. So, I have my cube here. So, the Fullerene molecule sitting in the cube corners these Fullerene molecules come very close. Just for the schematic I am drawing them a little far away. So, these all will be in orientation 1 O1, and the ones which are sitting in phase centers, which now the phase centers are not lattice points anymore in the orientationally ordered state, and they would be in orientation 2. And now this is my primitive cubic or simple cubic crystal. Now each lattice point having more than one Fullerene molecule. So, as we can see that Fullerene is a very interesting example in many senses, including the formation of an FCC crystal, a primitive cubic crystal, and also the very structure of the Fullerene molecule itself is very interesting to analyze in terms of the symmetry of the molecule, starting with the icosahedron. As you know that the icosahedral symmetry is inconsistent with the formation of crystals, and when you try to combine the symmetry of the icosahedral symmetry with the cubic symmetry, you can see that the symmetry of the structure is lowered, and actually you get the Pa3 bar kind of a symmetry in the Fullerene crystal. So, with this we come to an end of the sort of the consideration of ionic and covalent crystal. Next we are in a good position to start discussion about defects in crystals. Patel has a question before we proceed to defects in crystal.
As my knowledge, if a crystal have loose packing, I means packing fraction is very low, so they form some not too much hard crystals. But if we insert some CNT in polymer matrix, then on practically it's comes too much harder.
Okay, very important question.
What is the reason?
Okay, very important question. So we are asking about two concepts, and perhaps we should not confuse these two concepts. One concept is the concept of packing fraction, another concept is the concept of bonding. Okay. Now suppose I consider a FCC crystal like copper, which perhaps has a higher packing fraction than a crystal like diamond, like carbon diamond. But even though diamond has a lower packing fraction, it has much higher hardness. It is much more difficult to deform diamond, and this is coming from this covalent kind of bonding. Okay. Now with respect to specifically when you are talking about crystals and packing fractions, even though if I am the question you are asking is that now suppose I take a carbon nanotube or a fullerene molecule and I form a fullerene molecule crystal or put fullerene in a polymer matrix, what is the role they play and what is the role they play in deformation? That is the specific question we are asking, and especially with regard to a property like hardness. Now when you try to deform a fullerene crystal, you are actually trying to deform not the carbon covalent bonding, but actually you are trying to deform the van der Waals bonding. That is what will get deformed. Therefore the crystal will be very soft. In fact, it will have a low melting point because of this reason. Now when you are putting it isolated molecules inside a polymer matrix, when you are trying to, and assuming there is an isostrain condition, that means the fullerene molecule is nicely bonded to the polymer around it. When you are trying to strain the polymeric matrix, then the carbon bond which you will try to strain in the fullerene molecule would be the covalent kind of bonding, in which case it will actually show its good strength. Now this is very similar to a shearing of a graphene crystal. Suppose you try to shear a graphene crystal along the planes. So these are my graphene planes, and now I got the graphite crystal, I shear it. In this case I am trying to deform my van der Waals bonds, and it will actually show very low shear modulus. But suppose now I pull along the planes, that means now I have two options. Now I have my graphene planes here. I am not drawing them like hexagons, but these are my planes of graphene which form the crystal. So now suppose I am shearing my planes like this, my shear is this direction, then the van der Waals bond between the planes is going to be sheared, and this crystal is going to be extremely weak. On the other hand, suppose I pull along these two planes, the graphite planes, then actually I will be stretching the carbon-carbon covalent bond, in which case the crystal will be strong. Okay. So this, so we have to clearly make sure that along with packing fraction, now the reason for packing fraction, if you look at the macroscopic scale, there the definition of packing fraction is more like porosity, or what we might call the density of the material as compared to the theoretical density, right. In that case you keep on removing more and more of material from the thing, which is now a macroscopic picture. In that case obviously the modulus is going to come down, and that picture has not to be confused with the microscopic picture when you are talking about bonding and the kind of bonding you are distorting while actually getting your property. So let us now proceed to defects in crystals, and in this topic we will consider point defects, line defects, surface imperfections and volume defects, which we actually, this is itself a classification based on dimension, which is 0 dimensional, which are point defects, 1 dimension which are line defects, 2 dimensional which are surface or interface kind of imperfections, and finally 3 dimensional defects which are volume defects. Now before we actually take up some of these things, we will first start with the broad overview of the entire what you might call the classification of defects, and some of these so that you have a broad umbrella picture of what defects are and how do we classify them. This slide we have seen before, and we had already seen that we want to proceed from an ideal crystal like the case of a we have seen before, and you want to finally arrive at for what you might call a microstructure somewhere in between, and finally a component. We have to go through a concept of an important modification to the ideal crystal, which is now introducing crystalline defects. And now we had already seen, we had mentioned this clearly, that these defects play a very important role in determining the properties of a material. In other words, suppose I take and we will of course take up these examples very soon and we will consider them in detail, but To give a very important example, for instance, suppose I took a pure crystal and I tried to shear it, you will find that the shear stress would be of the order of gigapascals. But suppose there are defects in this material and we are specifically talking about a kind of defect which is known as a dislocation, then you would notice that the yield stress would be ordered by a few orders of magnitude. Similarly, suppose you took a very perfect ionic crystal, you would notice that it would, for instance, it could be colorless. But suppose there are point defects known as F centers, then you would notice that the crystal could be colored. So, many of these properties which could range from the optical to the mechanical to the thermal, etc., would be very much influenced by these defects, and therefore, it is very important for us not only to consider an ideal crystal, which we have done so far, and we also so far considered the definition of ideal crystal either based on purely geometrical entity or even a physical property. We also seen how we can sort of ignore the positional or the orientational order. We have seen that aspect also, but now we need to go to the what we mean called the real crystal with defects, which is the first handle on understanding the properties of real materials before we proceed to the other important stage, which is the stage of the microstructure. Now, when we talk about properties, there are something known as structure sensitive properties and the others which are known as structure insensitive properties. Now, the key word of course is the word sensitive, and the second key word is structure, right. Now, when I say structure, typically what we mean by the structure is microstructure, though in other contexts some people might use it to mean crystal structure or the electromagnetic structure, but typically when they say structure sensitive, they actually mean the word microstructure. And the second keyword, as I pointed out, is sensitive. That means that we are using the word sensitive and not dependent. To give an example, for instance, the density of any material would be depend on the concentration of vacancies. Vacancies, of course, as we shall see soon, are missing atoms. Typically, for instance, in a copper crystals, you will see that if you remove a copper atom from its lattice point, that would be called a vacancy. Okay. Now, if you remove more and more copper atoms, you will see that the density would decrease. But this is not a sensitive case of vacancies. The density would not change very much, and normally, for instance, suppose you take copper at room temperature, the concentration of vacancies would be very small, and this would not be something which would be the concentration of vacancies would not play a very important role in determining the density of the material. So, we have to remember that often there could be properties which are dependent on this defect structure, but we are not talking about those dependences, but we are talking about the sensitivity to the presence of those defects. Okay. Another example of the dependence or the sensitivity would be the elastic modulus would be a sensitive function of the dislocation density, for instance. Would not be a sensitive function of the presence of dislocations, but as we saw already that if you talk about yield stress, then the presence of dislocation plays a very important hand. Okay. Now, when talking about yield stress, then the presence or absence of dislocation makes a lot of difference to me with regard to yield stress. So, presence of dislocation would not, for instance, affect my density very much, it would not affect my elastic modulus very much, but it would affect my yield stress very much, and therefore, yield stress would be a structure sensitive property. And later on we shall see when we do dislocations that we are not merely talking about dislocations, we will talk about more details about this presence of this dislocation, how they are present, etc., would also influence my yield stress. So, whenever I am talking about a structure sensitive property, that means I need to understand the presence of my defects in the material and how they influence my property. And examples of structure sensitive properties would be, as I have seen already, one is yield stress, fracture toughness would be another property, structure insensitive properties would be examples would be density, elastic modulus, etc. Now, inadvertently or advertently, we had talked about defects and we had used a term perhaps in this conjunction, which is a very important term to understand, the term of defect structure. For instance, now if you read the last sentence here, in case of the structure sensitive properties, the defect structure in the material plays an important role in determining the properties. So, there is an important technical term or a technical phrase which comes in this context, which is not just defects, but defect structure. So, if you go back to the diagram before, if you can start with crystals, of course, you can talk and then talk about defected crystals, which means there are defects inside, but then we go to the next scale, which is known as microstructure. So, this is an important thing we saw, the microstructure, right. Similarly, we now do not want to just be talking about defects, but we want to use a more sophisticated language, which is the concept of defect structure. So, what do we mean by this defect structure? Because Of course, initially when we start a description of defects, we will start with isolated defects, maybe a single vacancy or a single dislocation, to understand what this defect is, what role does it play in altering perhaps the symmetry of the crystal or its properties. But soon we will have to understand not isolated defects but defect structures. Okay. So, what is this defect structure? Actually, it is a very complicated phrase to understand. It hides inside it a lot of details, okay, and is in some sense very similar, as I pointed out, to the term microstructure, which also hides in it a lot of details, and a lot of parameters actually have to be specified to characterize this term. And of course, the bigger goal would be not only to understand the defect structure, but to correlate it with the properties. Exactly the same way, not only we want to describe the microstructure, but we want to correlate the microstructure to the properties, what we typically we call the structure property correlation or the microstructure property correlation. Okay. Now, of course, this initial description would be highly insufficient to understand the entire term defect structure, but we will try to see what points go into the definition of the term defect structure. Now, I need to understand that what kinds of defects are present along with their dimensionality. So, I need to understand, say for instance, if there are vacancies, are there dislocations, are there grain boundaries which are present in my crystal now, or which go on to break up my crystal or break up the perfect symmetry in the material, and therefore, I need to understand the kind of defects present along with their dimensionality. I need to also understand the nature of these defects in terms of their origin. And we will of course take up some of these topics very soon and some of them slightly later, but we will try to understand these terms, which of course are the key words for our future discussions. So, I need to understand the nature of these defects in terms of their origin. Are they originating from, are they statistically present, or they have the structural origin? This is an important question I would ask, because now that would directly have an influence on the distribution of these defects in the material as well, apart from the role the defect would play on its properties. I need to understand the nature of these defects in terms of their position. For instance, are there random defects present somewhere in the crystal? So, there are no particular positional order, or they could even be ordered, like exactly the same way we have described, for instance, the ordering of alloys. So, these defects also could get ordered, and therefore, I would have an ordered crystal now, but now the entity which is getting ordered is not an atomic species, but actually a defect. And these were very, very important, and we saw that ordering actually leads to a change in symmetry of the structure and actually the structure itself. And the very recent example we considered was the orientational order with respect to the Fullerene crystal. Okay. And similarly, when defects get ordered, they change the symmetry of the crystal and the crystal structure, and correspondingly the properties. I obviously need to understand the density of these defects and the spatial distribution of these defects. So, this is a very important quantity. Suppose I am talking about vacancies, it is not enough I know, for instance, there are vacancies present in the material. I need to know how many of these lattice sites, a fraction of these lattice sites are vacant. That means I need to know its density. I also need to know what is the spatial distribution of these vacancies. In other words, suppose are these vacancies evenly distributed in the crystal? Are they, for instance, associated with each other forming a divacancy? Are many of these vacancies coming together in a particular crystallographic plane? Okay. These are questions we would like to ask, and all these questions become very important and pertinent in the description of defects and understanding the term defect structure. I need to understand the interaction and association of these defects with each other. Suppose I have a defect, like for instance an interstitial impurity atom. I need to ask this question, where is this interstitial impurity atom, for instance, positioned with respect to say for instance a grain boundary, say with respect to a dislocation line. So, these are questions I would ask, and therefore, for instance, if a interstitial impurity atom is positioned very near a dislocation, it would get into a low energy configuration, and now these two defects would get associated. Similarly, vacancies could get associated to form a divacancy. And what is the kind of interaction I am talking about between these defects? How does a point defect interact with a dislocation? How does a point defect interact with a grain boundary? So, these are questions I would ask, and therefore, I need to worry about the interaction and association of these defects with each other. So, needless to say, the task of understanding these properties based on defect structure is very difficult. So, this is actually a very difficult proposition, but then the starting point is very easy, that I start with each defect in isolation and then slowly start putting some of these defects together to understand the bigger picture. So, let me summarize this very important slide, because this slide tells you that I am starting with a perfect crystal. Of course, the way I define this perfect crystal, we have already seen that it could be not just perfect, I could mean in some of these reduced definitions which are shown by stars and double stars here, but no sooner than later I would like to proceed to real crystals wherein I introduce defects. One inevitable defect obviously is going to be the surface, because no crystal is infinite, therefore I need to truncate a crystal some point of time, and therefore I would have finite crystals. So, one inevitable defect we already seen. The other inevitable defect would be thermal vibration, because 0 Kelvin is unattainable, therefore at any positive Kelvin there are going to be some vibrations of atoms around their mean positions, their lattice positions. Therefore, thermal vibration is another unavoidable defect. Therefore, two defects are unavoidable in materials anyway, therefore it is better that I consider real crystals sooner than later. But I am talking about real crystals, that means I am introducing defects. I cannot talk about defects in isolation, or I need to characterize the defects a little more detail before I understand the properties. Therefore, I need to understand a term called defect structure. And I am talking about a defect structure, I am talking about the density of these defects, the spatial distribution of these defects, the kinds of defects present, what is their origin in terms of for instance, are they structural in origin, or are they ordered, for instance, are they disordered. So, I need to understand all these little details before I can understand the role the defect plays in my properties. And once I have this understanding, I am really in a position, for instance, to jump to some of the next level, which would be understanding microstructure in its entirety, and also for instance the behavior of a component. Now, as I pointed out to again, that we should always start with the simplest possible, that means we will start with a single isolated defect, try to understand its behavior in the crystal, then slowly go on to understanding these more complicated cases of defects in material.